This is Unit 4, Topic C. We're going to talk about antiderivatives. Now, it may seem to you that we have just spent a couple of sections talking about this idea of the integral and the area under the curve and all of its properties, and that we're just going to abandon that and go a whole new direction now. And actually, you'd be right, but I'm going to tell you, bear with me, because once we finish Topic C here, we're going to, in the next section, see the connection between what we did in the first couple of sections and what we're going to do today. So, antiderivatives. It is kind of just like it sounds. It's literally going backwards. In other words, if I tell you what the derivative of a function is, you're going to tell me what the original function was. So just using what we already know about derivatives, let's kind of use that thinking backward approach to determine the antiderivatives of each of these functions. So first of all, if little f of x is 3x squared, what's capital F? What function did you take the derivative of to get this? Well, that's the derivative of x cubed, right? So x cubed derivative would be 3x squared. We're just thinking backwards. What about cosine x? Well, that's the derivative of sine x. So capital F would be sine x, whose derivative is cosine x. E to the x is its own derivative. So the antiderivative of e to the x is still e to the x. And let's see, 7x would have derivative 7. The function whose derivative is 1 over x was the natural log of x. Again, just thinking backwards, what function has secant squared x as its derivative? Tangent x. And finally, what function had 1 over 1 plus x squared as its derivative? May have to think back a bit, or perhaps even use your little list there, but that is arctangent of x. Okay. So this is all just using the backwards derivatives, if you will. All right, while I have this table up here, let's just look at the question that's right below it. It says, is the antiderivative of a given function unique? So let's come back up here to this first one. We certainly know that the derivative of x cubed is 3x squared, but are there any other functions that also have a derivative of 3x squared? Actually, there's infinitely many. For example, x cubed plus 5 also has as its derivative 3x squared, since the derivative of the 5, the constant term, is 0. Or x cubed minus 7 would also have a derivative of 3x squared. Right? In fact, you could add or subtract any constant to any of these without changing the derivatives. So when we're doing antiderivatives, what we typically do is say the antiderivative of 3x squared is x cubed plus an arbitrary constant, any c you want. And that would be true for all of these. So as you'd start working with antiderivatives, get in the habit of always including that arbitrary constant term with every antiderivative. So is the antiderivative of a given function unique? No. We could add any constant without changing the derivative. All right, there's another name for the antiderivative. It's sometimes called the indefinite integral. And you see that word integral again, and you're going to see very similar notation as well. The notation looks like this, and I'm just going to use that very first one from the table again, the 3x squared. We say the indefinite integral, or antiderivative, they mean the same thing, of 3x squared dx is equal to x cubed plus c. So this integration sign without any limits, right? There's no numbers here like there were when we were talking about the area under a curve, stands for the antiderivative, often called the indefinite integral. And whenever you see that, you know you're just being asked, hey, what function is this the derivative of? Working backwards, we find the x cubed, and then don't forget that what we call the constant of integration, that arbitrary plus c, whose derivative is always 0. All right, let's talk about a few rules that are going to make doing antiderivatives a bit easier. First of all, power rules for antiderivatives. This is the exact opposite of the power rule for derivatives, right? Instead of decreasing the power by 1, we increase the power by 1. And instead of multiplying by the power, we divide by it. So there's our power rule for antiderivatives. Let's try it out a couple times. Here n would be 5. So my antiderivative rule says take x to the n plus 1, so 5 plus 1, divided by n plus 1, 5 plus 1, plus c, or x to the 6th divided by 6, plus c. Now you can always check an antiderivative. If I take the derivative of my answer, I should get back to here again. And notice if I did, this would become 6x to the 5th. The 6's would cancel, and I'd be right back here again. All right, just like with derivatives, oftentimes we have to rewrite the function that we want to take an antiderivative of in order to take advantage of that power rule. That's what's going to happen here. We're so used to this by now. Every time we see a radical, we rewrite it immediately as a fractional exponent, right? So that would be the integral of x to the 1/4 dx. N is therefore 1/4. And so using my antiderivative rule, I would get x to the 1/4 plus 1 divided by 1/4 plus 1 plus c. That is x to the 5/4. And usually instead of dividing by 4 5/4 to avoid the complex fraction, we'll just multiply by the reciprocal. So I'm going to make that 4/5 instead. And then I've got my plus c. Notice that I tried to differentiate. When I bring down the 5/4, 5/4 times 4/5, everything's going to cancel. It just becomes 1. X to the 1/4, which is exactly what I have here. All right, one more. The integral of 1 over x squared dx. Again, I need to write this as x to a power if I want to use this rule. So we'll do that. This would be x to the -2 dx. And that antiderivative would be x to the -2 plus 1 divided by -2 plus 1 plus the arbitrary constant. That's x to the -1st. Dividing by -1, I'll just pull the minus out in front, plus c. Just like the power rule for derivatives, you got so good at it you didn't even hardly have to think about it, you will find yourself getting to that same point with this power rule for antiderivatives. Increase the power by 1 and divide by that new power. All right, what about some arithmetic rules for antiderivatives? Notice these are the ones that we've seen also for definite integrals. They also work for antiderivatives like they do for derivatives and limits. Constant multipliers, can be brought outside the integral as a constant multiplier. And if I want to find the antiderivative of a sum or difference of functions, I can just do the two antiderivatives separately and then add or subtract them. All right, let's give that a shot here. In our example, I'm going to rewrite this first of all. The 2 is a constant multiplier. I'm going to bring that out front, times the antiderivative of x cubed dx. And then subtract, bring the 5 out front, antiderivative of x squared dx. Plus, I'll bring the 6 out front, antiderivative of x dx. Plus, I'm just going to leave that as the antiderivative of 3 dx. All right, I've got a bunch of power rules to do here. I'm going to start trying to do them a little bit more mentally. So I have 2 times. I increase the power by 1, so x to the 4th. And then I divide by that new exponent, 4. Now I'm not going to bother putting a plus c on this until I'm all the way done. I'll put my plus c on at the very end. I then have subtract 5 times. Again, using this power rule, that's going to be x to the 3rd power when I increase my exponent, divided by 3, plus 6 times. And keep in mind, that's really an exponent of 1. So when I increase my power by 1, I'll get x squared, and I'll have to divide by that too. Plus the integral of 3 dx. What function has derivative 3? It's going to be 3x, right? And now finally I'm done with all my antiderivatives, so I'll put the plus c on the end. All right, we're going to clean up the arithmetic a little bit, but basically we're done. I've got a 1/2 x to the 4th minus 5/3 x cubed plus 3x squared plus 3x plus c. And there we go. There's the whole antiderivative. All right, let's try a couple more. The second example here, right now is written as a product, and I don't have a rule for taking integrals of products. So I'll need to simplify that before I can do the antiderivative. So I'm going to start by just rewriting this as the integral of 3x squared. Negative 6x and positive 4x would be negative 2x minus 8 dx. Now I just have subtraction, and so I know I can do each term separately. I'm not going to rewrite the whole thing as 3 separate integrals this time, but mentally that's what I'm thinking. So I'd have 3 times, and then the integral of x squared. That's x to the 3rd over 3. Notice those 3's are going to cancel out, and yeah, that really is just the derivative of x cubed, right? We kind of knew that. Subtract 2 times, and again, keep in mind that this exponent is actually 1. So when I use my power rule, I'll get x to the 2nd over 2, minus the antiderivative of a constant 8 is just 8x, plus c. So I just end up with x cubed, minus those 2's will cancel, so x squared, minus 8x plus c. All right, I have a similar problem with example 3. Right now it's written as a quotient, and I have no rules for taking antiderivatives of quotients. So I'll need to do some algebra first. I'm going to show you something a lot of people like to do. If you want to, you can just take that x squared from the bottom and bring it up as an x to the -2, a multiplier. And then I'm going to write the numerator here as x to the 1/2 minus 3x. For people who don't like to think in terms of division, thinking of it as multiplying by x to a negative power sometimes makes the thought process a little bit easier. So if I now distribute this, because I still have a product, which I can't integrate, distributing the x to the negative 2 would give me x to the negative 3 halves minus 3x to the negative first. Now I've just got powers of x, so I can use my power rule. This one's going to become, let's see, if I add 1 to that exponent, it becomes x to the negative 1/2 divided by negative 1/2 minus 3 times. And we may be in a little bit of trouble here. When we add 1 to this exponent, we get x to the 0, which would tell us to divide by 0. And that's a big problem, right? That can't be. So I'm thinking this is wrong. In fact, I'm going to have you hold that thought for just a moment. We'll come back and finish this problem in just a minute. I'll throw the plus c on here so I don't forget. But this is actually the antiderivative of something you do know. If I rewrite all of my derivatives in their antiderivative form, notice if you read them backwards, they're your familiar derivatives, right? The derivative of sine is cosine. The derivative of secant, secant times tangent, etc. The one that we need is actually on this list. This, x to the negative first, is really 1 over x, right? So I should think of that as 3 times 1 over x. And the antiderivative of 1 over x, it's all the way down at the bottom here, it's the natural log of x. We usually put the absolute value in there sort of as a precaution to make sure we're not taking the log of a negative number, since that's not allowed. So when I see this, instead of using the power rule, I really should have just put in the natural log of absolute value x instead. Okay. Almost everybody at some point tries to use a power rule with that exponent of negative 1, so I wanted you to see it. Whenever that happens to you, whenever you get division by 0, get suspicious. You probably needed a natural log instead. All right, cleaning this up a little bit, I'll just use the reciprocal. So instead of dividing by negative 1/2, I'll multiply by negative 2 over 1, or just negative 2. X to the negative 1/2 minus 3 natural log x plus c. All right, so in addition to the power rule, we're now going to go ahead and say that this whole list of antiderivatives is fair game. Again, they're all just literally the reverse of derivative rules that we already knew, maybe with some negative signs readjusted. And those, by the way, are also in a list in your formulas packet that you can use on tests, so you can always refer to that. So let's go ahead and use those, and we'll look at a couple of examples on page 15, our next page. So if I want the antiderivative of 8 cosine x minus 5e to the x dx, it is subtraction, so no problem. It's not multiplying or dividing, thank goodness. 8 is a constant multiplier. And then I just want to do the antiderivative of cosine x, which is just sine x. I'm then subtracting, and again I have a constant multiplier of 5, and then the antiderivative of e to the x, that's an easy one to remember, it's just e to the x, right? I'll add my constant of integration, and I'm done. All right, take a look at the next example. 6 plus sine x divided by cosine squared x. That one looks a little scary right now because it's definitely a quotient, and I don't have any way of doing an antiderivative of a quotient. So I'm going to encourage you to keep in mind, sometimes using a bit of algebra or trig identities is helpful. I'm going to start out with some algebra on this one. As long as I keep my common denominator, I can split up this numerator as two separate fractions. So I can think of this as the integral of 6 over cosine squared x dx plus the integral of sine x over cosine squared x dx. Common denominator, so I could have brought those back together to get it right back what I started from. All right. Well, I'm not sure that did me any good, but we'll see. Cosine is the reciprocal of secant, right? That's just a trig identity. So I could, if I wanted to, bring that 6 in front of the integral. And then the reciprocal of cosine is secant. So since that was cosine squared, I would have secant squared x dx. That makes me a lot happier because that's one of the integrals on my list that I know, right? So I'm going to be all right with that one. Plus sine over cosine squared x. Now I could just make that sine x times secant squared x, but it's not helpful, right? Nowhere on this list do I see sine x times secant squared x. So true, not helpful. Instead, let's try breaking this up another way. I could think of this as sine x over cosine x. I don't mind that because that's tangent. Times 1 over cosine x. Right? If you multiplied these together, you'd get back what you started with, so we haven't really changed anything. And this now actually has some potential. I'm still going to just rewrite this for the moment. I'm not actually doing the antiderivatives yet. Sine x over cosine x is tangent x. And 1 over cosine x is secant x. That one I think is on my list. That's the reverse order, but that doesn't matter, right? The integral of secant x tangent x dx is secant x. So I've now got two integrals, both of which we know how to do. Again, the antiderivative of secant squared x was tangent x. And notice I brought that 6 along. And the antiderivative of tangent x secant x is secant x. I'll add my constant of integration, and we're good to go. All right. One last note here. Not all functions have antiderivatives. You're used to functions when you're taking derivatives, and honestly, as long as you follow the derivative rules correctly, you can find the derivative of any function. Every single function has a derivative. It's not possible to find an antiderivative for every function. Think about that one. Why is there no antiderivative for that? Well, the antiderivative of the sine function is minus cosine. So I could try minus cosine of x squared plus c. But if that's truly the antiderivative, I should be able to take the derivative of this and get back here. So let's check. We're wondering if that's true. If I take the derivative of minus cosine of x squared plus c, I've got my minus, and then the derivative of minus cosine is, or excuse me, the derivative of cosine is minus sine of x squared. So negative is going to make that positive. That's a good thing. But what else do I have to do when I take this derivative? I would also have a chain rule, right? The derivative of the inner function x squared would be a times 2x. And then the derivative of the constant is 0. So I actually get 2x sine x squared. That's not what I started with. I didn't have that 2x there. And so in fact, this did not work. Okay? There are lots and lots of functions that don't have antiderivatives. In fact, really only special ones do. We'll be working some more with those in the next video. We'll actually be taking a look at an application, I guess, in the next video. and then we'll go on to linking the two ideas, the definite integral with the antiderivative, in section D.